Okay, this little lecture will be on physical and chemical changes. So, the world and everything in it is constantly changing. Now, these changes can be simple, so it can be just like crushing a can, breaking a window, or turning this banana into a smoothie. Now, there can also be changes that are a little more complex. So here we have all these ingredients, and we can change these ingredients into cookies. And we've got these nice clean nails here, which can become rusty. Now, all of these changes are either physical changes or they're chemical changes. So let's start with physical changes. Now, physical changes can occur when a substance changes in some way, but it doesn't create a new substance. So it's still the original substance that it was. It just might look a bit different or it might behave in a different way. But really, it's exactly the same substance as it was before. Now, here I've got some examples. So water being frozen into ice cubes. So you can have water in its liquid state, freeze it into an ice cube. It looks different because now it's a solid, but essentially it's exactly the same thing. It's still water on the atomic level. Now, the same thing with Milo. You get the powdered Milo, you dissolve it into hot milk. Now, you would have done this in Year 7 with your separating mixtures topic. When something dissolves into something else, it's not actually bonding with the atoms. The atoms aren't joining together. What's happening is the atoms are sitting next to each other. Same thing with cornflakes. You get cornflakes in your bowl, they stay nice and crispy, leave them in there long enough, and the cornflakes go soggy. Nothing's changed. The atoms haven't changed. The cornflakes have just gone soggy, that's all. So they've just changed physically. Their shape has changed. Now, the best way to tell if an object has undergone a physical change is to focus on the states of matter. So you're all familiar with this. You've seen this in Year 7. We've got the 3 states of matter. You have liquid, a gas, and a solid. Now, in this example, they're using water. So we'll start with a solid. So solid water is obviously ice. Now, when a solid becomes a liquid, so it goes to liquid water, it undergoes melting or liquidification. It's a hard word to say, liquidification. Easier just to remember melting. So solid ice, it melts to produce water. Now, when water gets heated up enough, it'll undergo evaporation and become gas or a vapor. And in this case, it'll form clouds or steam. And you can see that in a hot cup of tea, you can see the steam rising off the tea. And even in cold weather, when you step outside and you can see smoke coming out of your mouth, that's the same thing. That's evaporation of the liquid in your mouth. Now, a very interesting thing that can happen is if gas is super treated with really cold temperatures, it can actually go straight from its gaseous phase straight to solid ice. Now, it's rare, it doesn't happen in nature very often, but we do see it when there is snow and hail. So most of the time in the clouds would build up, and once that temperature drops, the vapor in the cloud would start to condense. So here we're going backwards now. So we have gas and vapor, and we're condensing to go into liquid, and that would fall as rain. Now, occasionally what will happen is, especially in really cold temperatures, that vapor will go directly to a solid, and it'll fall as snow or as hail. And we experience hail more in Sydney than we do snow. And that process is called sublimation. Now, going along the reverse, again, we've got a liquid. And if we put that liquid into a freezer, we fill an ice cube tray up with water and we freeze it, it becomes a solid. Now, we also call it solidification. Again, you can just remember it as freezing. It's much easier. So an easy way to remember if a change is a physical change is to simply think about the changing states of matter. Has it gone from a solid to a liquid? Was it a solid and now it's a gas? Was it a gas? Is it now a liquid? Basically, has it changed shape? Is it the same thing, but it's just in a different packaging? The shape has just changed. Now we move on to something a little more complicated, and that's the chemical change. Now, chemical changes occur whenever a new substance is formed. So in this case, the atoms are actually bonding to each other and changing to form a different element. Now, remember in the last few lessons, I was talking about carbon, and we did that experiment where we burnt all the different objects and we were looking to see if we could see the carbon, and we could tell because they were going black. Now, carbon is coal. So the coal that we burn to produce our heat and our energy and our electricity and things like that is coal. It's essentially carbon. But a diamond is also carbon. Its atoms, or its little carbon atoms, are just bonded in a different way. Now, it's not a physical change. This is a chemical change. It's chemically bonded in a different way. So right down to the atoms, it's changed shape. The atoms bond differently. And so when that happens, you get a chemical change. Now, it's hard to see atoms. So how do you know a chemical change has actually happened? Well, these are the things to look for. Usually when we mix two chemicals together, we can tell if a chemical change is happening or whether they're just, mixing together and forming a solution. For one, a production of light. Usually you'll see big bursts of light, flashes, explosions, things like fireworks are chemical reactions. There's also a change in temperature. Usually it's an increase in temperature, so things get hotter during a chemical reaction. Then there's a change of color. So let's go to the next slide. So word equations. Now in a chemical change, the atoms in one or more substance rearrange. So just like I was mentioning with the carbon, in a carbon it's one form, but in a diamond, the atoms are arranged differently. They rearrange to form a new substance. Now, no new atoms are formed. They're just rearranged. So if I had a lump of coal that had 20 atoms in it and it changed into a diamond, I would have a diamond with 20 atoms in it. Okay, you can't actually create atoms out of nowhere. Now, there's a law that states that, now I've forgotten it. Now I'm thinking of Newton. I'm trying to record this in one go, so now I actually sound like I'm in the classroom forgetting all important things. I'll just move on, I'm sure it'll come back to me. So this is known as a chemical reaction. So the reactants are the substances present before the chemical reaction. So we have reactants and we have products. So before the chemical reaction, we have reactants. So we have the two things that are going to react together. Then we have the products. So when those two reactants have acted together, they produce a product. Okay, and we can see this a little more clearly on the next slide. So when scientists actually write out chemical reactions, we like to do it in two ways. The easiest one is a word equation. So look at this word equation. You have hydrogen, you have oxygen, and this arrow means that it's creating something. So it's a reaction producing. We don't use equal signs, we use arrows. So the arrow produces water. So hydrogen, oxygen produces water when they're bonded together. So here, the hydrogen and the oxygen are the reactants. They're the two things that are going to react together and they're going to produce a product of water. Now, word equations are basically that. The equation is written in words. So we write out the whole word hydrogen, whole word oxygen, whole word water. Now, to make things a little simpler for scientists, like we like to write in code, we don't want to write out whole big giant words. We as scientists rely more so on chemical equations. So you'll notice that these are the chemical symbols, just like they are on the periodic table. Now in this case, H for hydrogen, O for oxygen, and H2O, you guys know, is the symbol for water. So let me just explain these numbers that are here. And let me start with the H2O. When numbers are written in subscript when it comes to chemicals, now this is subscript when it's actually below the line of text, like a submarine. So when it's in subscript, it means that whatever letter comes before it, there's more of them. So in this case, hydrogen 2 means that there are 2 hydrogens. Oxygen doesn't have a number, so it means there's only 1. So there are 2 hydrogens and 1 oxygen. So 3 atoms all together and they're bonded together, and that produces water. Now, over on the other side where the reactants are, we have hydrogen and we have oxygen. Now, when a number comes before a large letter, and it's written up normal size, it's not, subscript down here, so it's not like below, it's up here and it's large, that's just telling you how many there are. Now, I know this gets really confusing, and it is an advanced thing to remember, this balancing of equations, but it's just something just to keep in mind. It's not going to be assessed. It's something that you focus on more in a year 11 and 12, but a few of you might be interested to know why it's here. So this is how we would draw water, always H2O. We like to make it very clear to say, well, there are 2 hydrogens here. I'm going to let you know that in the reactants, there's going to be 2 hydrogens as well. Because remember, we can't create atoms out of nowhere. Now, I'll set up another tutorial for those of you who are interested in the extension. And the extension will be on how to balance these equations and what they actually mean. It's completely optional. So don't worry if you're a little confused about what I'm talking about. All you need to remember is this part. So the H2O and the 2 of a subscript means that there are 2 hydrogens and 1 oxygen. So that's all you guys need to know. All right, so that's the end of the slide. I hope this tutorial was useful.